Have you ever stopped and wondered how your computer actually understands what you're asking it to do? When it sorts your photos, or finds a specific word in a huge document, or even just checks your password? Well, it all comes down to a special kind of language, one built on pure, unshakable logic. And today, we're going to build that language together, from the absolute ground up. This is the very foundation of how machines think.
So it really all boils down to this one single question. How do we take a complex idea, something like find all the email addresses on this page, and translate it into a set of simple, foolproof rules that a machine can follow without ever getting confused? To answer that, we have to start smaller. I mean, much, much smaller.
Think about it like this. You can't build a house without individual bricks, right? Well, the entire universe of computation is built from just a few simple foundational ideas. We're going to assemble these ideas piece by piece until we have a complete framework. So let's get started and find our very first, most fundamental brick.
All right, section 1, the atomic building blocks. Our first step here is to define the absolute smallest, most fundamental units we can possibly work with. You can think of these as the atoms of our new language.
And here it is, a symbol. This is our atomic element. You literally can't break it down any further. A 0 is just a 0. The letter A is just an A. And this is a super critical first step, because to give a computer instructions, we need a set of basic units that are completely unambiguous. A 0 is always a 0 and nothing else.
Now, if we collect all the symbols we're allowed to use for a specific problem, we get what's called an alphabet. In formal notation, we use that Greek letter, sigma, to represent it. But honestly, just think of it as our toolbox. And a really common alphabet, maybe the most famous one in computer science, is the binary alphabet. Its toolbox contains just two symbols, 0 and 1. Okay, section 2, creating sequences from symbols. So let's take stock. We have our atoms, our symbols, and we have our toolbox, our alphabet. Now we can finally start building things. And the most basic thing we can build is a sequence.
And that's called a string. A string is just a finite sequence of symbols that we've pulled from our alphabet. So if our alphabet is A, B, then Aba is a valid string. So is just A by itself, and so is Baba. It's just like using letters from the English alphabet to form words.
Now, this next idea is a little weird at first, but it is incredibly important. Most strings have a length, right? The string 011 has a length of 3. But there's one very special string called the empty string, and we represent it with the Greek letter epsilon. It's the only string in the universe with a length of 0. It might seem strange, but it's absolutely crucial for defining rules, like a sequence can have 0 or more characters.
All right, section 3, defining a formal language. So we've got symbols, alphabets to hold them, and strings made from them. The next level of organization is to group these strings into meaningful collections, and that's what we call a formal language.
So what is a language? It's simply a set of strings. That's it. Think about the English language. It's a set of all the words we consider to be valid. A formal language is the exact same idea. We're defining which strings are the correct or valid ones that our machine is supposed to recognize. And languages really come in two main flavors. A language can be finite. For example, the set of all binary strings that are exactly 2 characters long. There are only 4 of them, 00, 01, 10, and 11. That's it. The set is complete. Or a language can be infinite. Imagine the set of all binary strings that simply start with a 0. Well, that list just goes on forever. Section 4, organizing and counting our creations. We've established what strings and languages are. Next up, we need some power tools to help us organize, categorize, and count these creations in a more formal and, well, powerful way. This is called the powers of an alphabet. And don't let the notation scare you. When you see sigma to the power of n, it just means the set of all strings of length exactly n. That's all. So, sigma squared for the binary alphabet is the set of all strings of length 2, 00, 01, 10, 11. Sigma cubed would be all strings of length 3. It's just a very precise way to group strings together. And when we want to talk about the size of these sets, we use a formal term, cardinality. It's just a fancy word for how many things are in this collection. So, what's the cardinality of our binary alphabet? It's 2. And the cardinality of sigma squared, as we just saw, it's 4. And this all leads to a simple but incredibly powerful formula. If you want to know how many strings of a certain length you can make, you just take the size of your alphabet and raise it to the power of that length. This lets us calculate the size of these sets instantly, without having to write them all out one by one.
And this chart really brings that formula to life. Just look at the bars. With our binary alphabet, an alphabet of size 2, we start with 2 strings of length 1. When we go to length 2, the number of possible strings doubles to 4. At length 3, it doubles again to 8. This explosive exponential growth is a fundamental concept in computer science, and you can see it happening right here. Section 5, the universe of all possible strings. So we've grouped strings by length. But what if we want to talk about all of them? Every single possible string of every single length, all at once. For that, we need one final, all-encompassing concept. This is sigma star. It is the ultimate collection, the set of every string of every possible finite length that you can create from a given alphabet, from length 0 all the way to infinity. It is quite literally the universe of strings for that alphabet. Now, that idea of every possible string might sound huge and intimidating, but it's actually built in a very logical step-by-step way. You start with the set of strings of length 0, which is just our friend the empty string. Then you add in all the strings of length 1. Then you add in all the strings of length 2, and so on forever. It's just the infinite combination of all the smaller sets we've already talked about. Okay, section 6, why this vocabulary matters. Whew, that was a lot of definitions. Symbols, alphabets, strings, languages, sigma star. So why did we just build this entire vocabulary? What's the point of all this?
And here's why it all matters. This entire framework is the precise language we need to talk about the machines that process information. When we build a simple computer, or what's called an automaton, its whole job is to read an input string and decide, does this string belong to the language I care about? Without these precise terms, we couldn't even clearly define the problem, let alone design a solution.
So let's just recap for a second. We've gone from the tiniest, most basic symbol all the way up to the entire universe of strings. We've successfully built a complete mathematical vocabulary for describing the inputs for any computational problem. We now know exactly what a formal language is. And that, of course, leaves us with the ultimate question. Now that we can perfectly define a language, how do we actually construct a machine that can read any given string and tell us, yes, this is in the language, or no, this is not? Well, that is the fascinating question we're going to tackle next.